Welcome to the class. Dear students, today we are going to see what is resonance and what is resonance stabilization energy. Resonance. Resonance is the delocalization of pi electron. Very simple. It is the delocalization of pi electron in a molecule. Now this is a pi electron. These are 6 pi electrons, right? So it is making a complete full round and this pair of electron is coming here. Correct? So resonance, this is because of resonance. Now resonance or delocalization of the pi electron results in structures that differ with respect to position of double and single bond. See, the double bond was here, now the double bond is here, right? So these structures are because resonance is taking place, because delocalization of electron take place. Right, and because of this it results in different structures of the same compound, structures that differ in the position of single and double bond. As these structures are because of resonance, owing to resonance or owing to delocalization, therefore these structures are called as resonance contributing structures. They are also called as canonical forms. Okay, now the second point is, at any given time the structure of benzene, if you look through an X-ray diffraction machine, the structure of machine is neither structure number 1 nor structure number 2. Then what it is? Yes, it is a combination of these structures, right? So as it is a hybrid, as it is a combination, as it is a hybrid of these two resonating structure, the real structure is called as the resonance hybrid structure, because it's a hybrid of the resonating structure. So it is called as a resonance hybrid structure. Fine. Now to prove that benzene is really a resonance hybrid structure, X-ray diffraction measurements do prove it. How do they prove it? Let's see. See, if it is a carbon-carbon single bond, the length of that bond is 1.43 Armstrong. This we have observed in your ethane. If it is a carbon-carbon double bond, we have observed in ethene that then the length is 1.39 Armstrong. Now if we measure the carbon-carbon bond in benzene, that is somewhere in between 1.43 and 1.39, that is 1.34 Armstrong. So that means that it is actually intermediate between these two bonds. That means that the structure of benzene is a resonance hybrid structure, right? So each carbon-carbon bond is intermediate between a single bond and a double bond, right? It is an intermediate between a carbon-carbon single bond and a carbon-carbon double bond. It is an intermediate between a sigma bond and a pi bond. So that explains the unusual and exceptional character of benzene and all those compounds that show resonance. That is why all the compounds that show resonance, they have got unusual behavior, exceptional stability. That is because it is something that is intermediate, which we are not expecting. So that explains the unusual behavior. Now next point is that the fourth point is that resonance, okay, what did I say? Resonance or delocalization of electron leads to extreme stability of benzene. Resonance, the phenomena of resonance leads to exceptional stability of this compound, of this molecule or of this compound. How it leads to exceptional stability? See, suppose you assume that here an electrophile is waiting to attack it, right? It needs electron, right? If the structure of benzene is like this, if the electrons are localized, it can easily take the electron pair, right? Doesn't have to do anything. It has to take an electron pair. But here, when it is a resonance, when there is delocalization of electron, it is extremely hard to take a pair of electron. So that, right, it is extremely hard. Okay, it's like an immature player trying to take football from a group of mature players. So they are rolling that football. So it's extremely hard for the electrophile to take electron from such a structure where delocalization is occurring, and that makes the benzene very stable. That makes the benzene unreactive, right? Exceptional unreactivity to electrophile, right? So that makes the benzene very stable. Now to illustrate and to prove in a much better way that there is actually stability associated with resonance, let us see the heat of hydrogenation of benzene. Okay, let us see heat of hydrogenation of benzene, and we can prove that really benzene is very stable because of resonance. We can prove that. Let us see. So let me draw the diagram. First, this is your cyclohexane. Here also a cyclohexane, and here also I draw. Okay. So here we have got a cyclohexene. So this is cyclohexadiene, and here I draw the hypothetical structure of benzene. Let me, because it is hypothetical, let me draw it in dot. This is the hypothetical, it doesn't exist. Okay, this is cyclohexatriene or hypothetical keccule structure of benzene. It doesn't exist. Okay, and here is our benzene. Now let me go for this. This is 28.6 kilocalorie per mole. Now heat of hydrogenation means that hydrogenation is a process, is an exothermic reaction. Exothermic reaction means the heat is evolved when hydrogen is added. So we add hydrogen and heat is evolved. So it's a measure of stability. Okay, how much energy is evolved out? Okay, so that measures the strength of this bond, double bond, right? So that will give you an idea. So for cyclohexene to be converted into cyclohexane, where there is only one single bond, a mole of this cyclohexene would evolve 28.6 kilocalorie per mole. For cyclohexadiene, the energy to convert it into this is 55 kilocalorie per mole. For your hypothetical structure of benzene or cyclohexatriene doesn't exist. We are just assuming it exists. These things don't exist. We are just assuming that this is existing, right? For that, it will be 86 kilocalorie per mole if it is to convert into this. Okay, and for benzene, if it is to convert into this, it would require only 50 kilocalorie per mole. 50 kilocalorie per mole. So as I said, heat of hydrogenation is the energy evolved when it is hydrogenated. When it is hydrogenated, actually this double bond breaks. So we will come to know the energy of this double bond, right? So it is 28.6 kilocalorie per mole for this one, cyclohexene. For this one, cyclohexadiene, it is actually into 2. So we will get somewhat about in this range, 55 kilocalorie per mole to convert into this. Now for this hypothetical structure, this doesn't exist, so we cannot calculate it practically. So theoretically we can assume just multiply it into 3. So you will get somewhat value like this, 86 kilocalorie per mole. So that is the energy required to convert this hypothetical structure into this, right? Now for benzene, to convert benzene into this cyclohexane, you need only 50 kilocalorie per mole. What do you understand by this? There are two things that we can understand. Number one, benzene's structure is not like this. It is not a keccule structure. Had it been a keccule structure where the electrons are localized, it would have evolved 86 kilocalorie per mole of energy. Had the structure of benzene been like this, where there is no delocalization, then it would have evolved 86 kilocalorie per mole. But it is evolving only 50 kilocalorie per mole. That means that the structure of benzene is not like this. There is really resonance taking place in the benzene ring. There is really, the structure of benzene is a real resonance hybrid structure. The real structure of benzene is a resonance hybrid structure. Had it been not, then this much energy would have evolved. Now, what is the difference? This difference, that is called as the resonance stabilization energy. So that difference is about 38.6 kilocalorie per mole. Now this difference between this one 38.6 kilocalorie per mole. So that is the difference had the structure of benzene been like this from this. So that is the difference, that is this energy minus this energy, that is the stability that is conferred to benzene owing to its resonance. Correct? That is the stability or resonance stabilization energy that has been gifted to benzene owing to its resonance. It's a benefit only, right? It's an advantage. That is an advantage that is gifted to benzene owing to its resonance. Right? So what is resonance stabilization energy? We can define from this diagram only. Resonance stabilization energy is the difference of electronic energy. Why I am saying it electronic energy? Because it is involved electron movement, right? Electrons are in dynamic motion, so there is energy associated with it. That's why I am calling it electronic energy. It's a difference of the electronic energy between the hypothetical structure of the hypothetical contributing structure with the real structure of any molecule. What did I say? Resonance stabilization energy is the difference of electronic energy between hypothetical contributing structure and the real resonance hybrid structure of any molecule. So that is resonance stabilization energy. That is resonance stabilization energy. Now let us see other examples of resonance. It is not that only benzene shows resonance. A lot of small simple molecules are also showing resonance. Look at the second example here. We very well know this. What is it? Yes, a carboxylate ion. It shows resonance. Look at this, right? So it can go here, this electron can go here, and this can come here, this can come here and yield back this, correct? So the the hybrid structure is like this, O on both sides, right? And negative energy is getting, the electrons are getting delocalized here. It is getting delocalized, right? So here we are seeing that because of delocalization of electrons in the carboxylate ion, two structures result, structures that differ with respect to each other in the position of single and double bond. These structures owing to resonance are called as the resonating hybrid structures, and the real structure of carboxylate ion is neither this nor this. It is a combination of these structures. It's a hybrid of these resonating structure, which is referred to as the resonance hybrid structure of the carboxylate ion. This is actually very stable compared, right? It gives stability. This delocalization of electron, it gives stability to your carboxylate ion. With the result, just look at this, your aldehyde. Is there any resonance in aldehyde? No, right? Is there any resonance in ketone? Look at this. It can go above, right? So negative charge can come on oxygen. No. So with the result, it can be easily reduced. Aldehyde and ketones can be easily reduced because the electrons are localized. But here it cannot be easily reduced, right? Carboxylate ion cannot be easily reduced. So this explains that aldehyde and ketones can be easily reduced while carboxylate ion are not easily reduced. This is because of resonance in the carboxylate ion. Right? Now let us look at one more example. Very simple molecule. Look at this. SO2. This is an example of resonance, right? This can come here and this electron can go here. Now the real structure is like this. I am reminding you, dear students, that this bond is an intermediate between the sigma bond and the pi bond. It's neither a sigma nor a pi but an intermediate between these bonds. So here also we have seen that SO2 it is showing resonance. Let us go for another example, a very famous example. 1,3-butadiene, conjugated diene it is, 1,3-butadiene. Let's show how it shows resonance. Look at this, right? This is 1,3-butadiene, right? So here what can happen? This can happen, correct? So it can lead to the first structure like this. Double bond will come here. This CH2 minus will come here, here plus will come. Another structure is also possible, right? In that structure this would come here and this would go here. So negative charge now will come. So this is 1,3-butadiene. We have it in our syllabus, B Pharm syllabus also and Pharm D syllabus also, how the stability of conjugated diene, right? The stability of 1,3-butadiene. So resonance explains the stability of the 1,3-butadiene. From that I have taken it as an example of resonance. So this is also an example of resonance where the positive and the negative charge are getting delocalized. Now one more example of resonance which is very famous is for phenoxide ion, right? Phenoxide ion also shows resonance. How it shows resonance? See, this is phenol OH. After it loses H, because it is acidic, it becomes negative, and this can come here. What is the second structure? Oh, I'm explaining, giving you all these structures so that you can get a better idea of what is. So many compounds do show resonance. See, these are all resonating structures of phenol, right? All we are studying in different chapters. Right? And now this comes back. There are how many structures of the phenoxide ion? Lot of structures, 5 structures, right? 5 structures of the phenoxide ion. So what is the overall hybrid resonance structure of phenoxide ion? Yes, negative charge is overall, and here, right? This is the overall resonance hybrid structure for the phenoxide. So phenol also shows resonance. Now let us go to another example so that you understand resonance in a much better way. Another example also I will show, but here electron is not getting delocalized, positive charge will get delocalized. I will show you that example. Look at this example of benzaldehyde, right? Now this can go here because it is electronegative. When this goes here, carbon may become positive. To negate that positive charge of carbon, this bond may come here. Look at this, right? Look at this. Now double bond comes here and positive charge will come here. Now what would happen? This can happen. Positive charge will go here in the next structure, right? Yes. Now what can happen? Yes, it can come here and positive charge will go here. So you get another structure. All these, see. Now what can happen? This can come back, right? And when this comes back, I forgot to put the negative sign here. Pardon me. Yeah. So when this comes back, this double bond will come back here. So what you get? C double bond O, H, and one full round has been completed. So what is the resonance hybrid structure now? Right? Positive everywhere. O, right? Correct? So now we are seeing that this where this example benzaldehyde where electron is not getting delocalized. What is getting delocalized? The positive charge is getting delocalized and it is forming a carbocation. Now its benzene carbocation or a benzene cation is called as a Wieland intermediate. So a Wieland, it's forming Wieland intermediates, and there are so many resonating structures of Wieland intermediates, number of resonating structures of Wieland intermediates. The more important thing is that positive charge is getting delocalized, and that is giving enough resonance stabilization to this benzene carbocation or to this Wieland intermediate. Now there is one more example, a little example which is very interesting. That is, resonance has a big role. It is the sole determining factor in governing or in determining whether nucleophilic substitution reaction in allylic and vinylic substrate. It is a sole determining factor that decides whether nucleophilic substitution reaction will take place in allylic and vinylic substrate. This is the allylic substrate, okay, allylic halide, and this is the vinylic halide. So this is the allylic halide, this is the vinylic halide. Resonance decides whether nucleophilic substitution will take place in allylic halide and vinylic halide. Actually, to tell you, allylic halide nucleophilic substitution will take place through SN1 mechanism, and two products will be formed. That will be 1,2 substituted product and 1,4 substituted product. So the main thing is that this product is formed because there is resonance of the carbocation. Actually this forms a carbocation. Okay, so this forms a carbocation. Like if Cl is going, then it forms a carbocation like this, right? So it can show resonance. The next carbocation will be some like this, right? So sorry, the positive charge will come here and double bond will come here. So two carbocations are formed. Now if OH minus is attacking, the nucleophile is attacking, two products will be formed. One will be 1,2 substituted, the other is 1,4 substituted. This occurs because there is resonance. These products come because there is resonance in the carbocation. So it plays a major role in nucleophilic substitution reaction of allylic substrates. For vinylic substrate, here nucleophilic substitution reaction doesn't take place. This is also because of resonance. Because what is happening here, this is going here, this is going here, and what would happen, this bond, it becomes stronger than carbon halogen bond. Normal carbon halogen bond may not be that much strong, but when this comes here, the carbon halogen bond becomes very strong. Okay, so X doesn't leave. If X doesn't leave, OH minus wouldn't attack it. So that is why, because of resonance here, nucleophilic substitution doesn't take place. But because of resonance here, nucleophilic substitution does take place. It takes place through SN1 mechanism, and two products are formed. For knowing that this aspect, for knowing nucleophilic substitution, please refer to my earlier video where I have discussed nucleophilic substitution reaction of allylic substrate in a separate video and nucleophilic substitution reaction of vinylic substrates in a separate video. Dear students, this ends up resonance. We have given various examples of resonance. We have seen how resonance gives immense stability to benzene and other compounds that show resonance. If you like the class, if you have understood it, please do not forget to subscribe the channel. Please like and share it with your friends. Thank you very much.